out with like what type it is, what the original points are, and then how those points got transformed. So the first one is quadratic, and they're pretty easy to spot, just anything that has an x squared. If there's an exponent of 2 in there somewhere, then it's going to be quadratic. So knowing that it's quadratic will tell us what points to start with. So we start with these 3 points. These are the parent function points for just the original quadratic with no transformations made to it whatsoever. Okay, so you guys should be looking, first of all, to see if the transformation is on the outside or on the inside. So that -3, that's the transformation, because that's something different from just the original parent graph. Because the original quadratic is just y equals x squared. So you guys should be comparing like what's different about the equation. And here the -3 is the add-on, and that's on the outside. Inside would be like parentheses x minus 3 with a squared on the outside. So this is an outside transformation, which means it affects y. And when it affects the y, it does exactly what it looks like it's going to do. So when you see a -3, it actually does subtract 3 from all the x values. I'm sorry, from all the y values. So subtract 3 from your y values, but then your x values won't change at all. So go through, take all the y values, and subtract 3. And you'll get this new set of ordered pairs. Okay, so plot the new set of ordered pairs, and that will be your new function. So that's this part. We're doing the sketch the function part right now. Okay, so those 3 points, please be super careful because quadratics and absolute value, they have the same 3 points, but the shape is a little bit different. Quadratics are kind of rounded and smooth like a U-shaped curve, and absolute value is pointed at the bottom like a V. So this is quadratic, which means when you go through these points, try your best to make it rounded off and smooth rather than like a sharp point at the end like absolute value would be. So the graph itself looks like this. You don't have to draw the original, but I just want to show you what it looks like for comparison. So this is like just the original quadratic function before you transformed it, and that might help you to recognize like, oh, this is how it looks different, this is what my transformation must have been. So when it says describe the transformation, for this one you would write something like this: shift down 3 units. And so when you write something like that, it's just describing how your new graph is different from the parent graph. So it's like picking it up and just moving it down 3 units on the y-axis. Okay, so 2 parts to your answer. You'd have this description and then the new graph. All right, part B. This one starts off being absolute value. Absolute value is easy enough to spot because you should see the actual absolute value bars somewhere in your equation. So this one is absolute value. And you actually start with the exact same 3 points as the quadratic had. Like that. Linear has a different set of points. Linear has a -1 right here, but that's the only difference. Other than this -1, the rest of the points are the same. So all 3 have 0, 0, and 1, 1. So this one, our original absolute value graph is just y equals the absolute value of x. So the difference here is there's a 1/2 out front compared to this one. The 1/2 is on the outside. Inside would literally mean it's inside of the absolute value bars, but it's not. It's on the outside. So being on the outside affects the y value, and it does exactly what it looks like it's going to do. So here there's a 1/2 being multiplied by our function, so that means we're going to multiply all of the y values by 1/2. It's like this, and then 0 times 1/2 doesn't do anything. So I went through and multiplied all my y values by 1/2, and then you'll plot those new points. The new points are right there. -1, 1/2, 0, 0 right at the origin, and then 1, 1. So now this one is absolute value. That's the one that should be like sharp and pointed down at the bottom. So not curved, not rounded, but that one should come to a sharp point like that. Okay, and again, just for comparison's sake, the original absolute value graph looks something like this. So whenever you have something being multiplied, that is either a stretch or compression. So this one is a compression because it's 1/2. So it literally cuts all the y values in half. So it's like taking the original function and just kind of squashing it. So it compresses it, it kind of gets a little bit wider. So this is called a compression. It's a compression by 1/2. So that would be your description. If it's stretched out, you'd say like it's stretched by 3 or stretched by 2 or something like that. But this is compressed because it's a fraction. So it kind of squashes the whole graph down. Okay, so that is number 18. Questions on that? Okay, then I have 16 votes each for number 15 and number 21. So let's do 15 first, and then we'll flip back to 21. So 15 is our piecewise graph, so you guys will definitely see one of these. So start off setting up your coordinate system, and we're going to block off our 3 different regions. So we have region A, and B, and C, and then each one of those regions has its own function. So starting with region A, it's supposed to be for only x values that are less than or equal to 0. So mark on, here's an x value of 0. So that blocks off, and then anything to the left. These are all less than or equal to 0. So this is region A. It starts here and then goes off to the left. So x is less than or equal to 0. That's region A. Region B, this 3-piece inequality, says that x is in between 0 and 2. So region B will start at 0 and then end at 2. So I'll go over to 2, drawing a little dotted line there. So this is region B, and it's just sandwiched in between those 2 values. Won't go any farther to the left or to the right. And then C is listed as x is greater than or equal to 2. So C starts at x equals 2 and then goes off to the right. So C starts here and goes to the right like that. So those are your 3 separate regions to remember in your graphing. When you graph function A, it should only be in region A. And same thing with B and same thing with C. So when you guys are setting these up, we're going to plug in some points, get some different ordered pairs, and then we can plot them. So starting with A, our function for A is h of x equals 1/3 x. So that's just the function that's listed right here. And that's just for our first region. Okay, so for this one, it says x is less than or equal to 0. That means you can only plug in regions that are in here. That's it. Cannot plug in any positive values. And we always start with the endpoint. So whichever one they mention right here, that's the endpoint. So that's got to be plugged in for sure. So we're going to plug in the 0. So h of 0. So remember, this notation just means to plug in 0 for x, or whatever I put in parentheses. That's what you're plugging in for x. So we have 1/3 times 0, and 1/3 times 0 just comes out to be 0. Okay, so that turns into an ordered pair, and that's the first ordered pair that we're going to be plotting. So 0 is our x value, and then what we got out was also 0, so that's our y value. Okay, so that's the first ordered pair. Next detail we need to be really careful about is when we're right on this boundary line, we need to know whether the point that we're plotting is going to be open or closed. So this one, because its x is less than or equal to 0, it would be a closed circle. So right on the boundary line, right at the origin, we're going to put a closed circle. And then you always need a second ordered pair, and the second ordered pair has to be somewhere in this region. Okay, so you could plug in, -1 or -2, -3, whatever you want, as long as it's in this region and not in regions B or C. So say we do, just -1, or you could do -2 or -3, whatever you want, as long as it's in that region. So this time we replace the x with the -1, and then our y value would be -1/3, because it's 1/3 times -1. So that's a new ordered pair. The x value is what we plugged in, and then the y value is what we get out. So that's the second point that we can plot. So if that's -1, -1/3 would be like here. So just a little bit down. And then when you're within the region, you don't have to worry about whether the circle is open or closed, because when you're safely within a region, it's just a normal point. It's only if you're on the boundary line that you have to worry about whether the circle might be open. So we start here with this point, and then the graph just goes off to the side like this. Only in region A, it stops when it gets to region B, and it does not go any further. Okay, so that's the first part. First little ray that goes off to the left. And then region B is going to be a segment in between those 2 values. So start with this function now. So our function for this middle part will be 2x minus 6. Okay, so now this one, when you're dealing with a segment you have to plug in this value and this value. So for the segment in the middle, they'll just give you the two values that we plug in. So you plug in 0 and you plug in 2. So plug in 0, so we'd have 2 times 0 minus 6. So that leaves us with -6. So x is what we plugged in. Y was what we got out. That's the first ordered pair. And then I also plug in my other endpoint, which is 2. So 2 times 2 minus 6. 2 times 2 is 4, minus 6 is -2. So I plug in 2 and I get -2. So that's my ordered pair. So these ones in region B, if I look carefully back here, this is just a less than, this is just a less than, so those will both be open circles right on the boundary. So when I plot this ordered pair and when I plot this ordered pair, they will both be open circles. So 0, -6 will be right here. Mark it with an open circle. And then 2, -2 will be right about here. Also mark that with an open circle. So these ones, this is just a segment. Remember, you can only be in region B. If you go any farther to the left, you're in region A. If you go any farther to the right, you're in region C. So make sure you stay just at that little segment in between the two dotted lines. Okay, so that's B. Last part is C, and this function is just h of x equals 1. So remember these ones, if it's just a number, that means no matter what you plug in for x, you're going to get 1. The y value will always be 1. So I start by plugging in 2, because 2 is my endpoint. It's the one that was mentioned right here. It's the boundary line on my graph. So I plug in 2, and just the way the function's set up, I automatically get 1. Whatever you plug in, you automatically get 1. And that's just the way this function is written. So my first ordered pair is 2, 1, and then you can plug in anything else that you want as long as it's in region C. So we could also plug in, let's say we want to plug in 5. 5 falls in region C. And the way this function is written, it says no matter what we plug in, we're going to get 1. So we plug in 5, we get 1. So that would be our second ordered pair. So last little detail is right on the 2. This is greater than or equal to, so this first ordered pair will be closed. So go to 2, 1, this is going to be a closed ordered pair. And then I also have the point 5, 1, which will be right here. And that's just going to be a horizontal line that goes off to the right. Because if the function value is always 1, it's just a straight horizontal line. It does not ever change from being a y value of 1. Okay, real quick, we got domain and range for this one. Let me sneak it in the bottom here. Domain is all reals, and I think I've used this notation before, the double line with the R. So it looks like the letter R, except it's got this extra little vertical line. That's just the symbol that stands for all reals. So if you want to be lazy like I do, you can just write that instead of writing out all reals. So this one, all of the x values get covered. This arrow goes all the way off to the right. I'm sorry, to the left. This one goes all the way to the right. And then this segment kind of picks up any missing x values that these ones have. So every x value will eventually get covered at some point in the graph. Yes, sir?
Is there a time when the domain is not real?
Yeah, if there's a gap, and we have seen that before where there's in between two dotted lines, there's a gap where you're missing a chunk of x values. That could happen. It's a lot more rare. Usually it's all reals, but I would be careful and just double check that there's no gaps or anything. All right, and then range. Remember I told you guys with range, you're just kind of moving up and down the y-axis, see if there's any gap, see if there's any point where it just stops. So this arrow over on the left will keep the graph going down and down and down forever. And then when we go up, it hits 0 and it just stops. And then it jumps to another value. So we hit this 0, which means it can be anything 0 or below. So start with that. It can be anything 0 or below. So that's what our first part of the range would look like. Anything less than or equal to 0. And then it jumps up to 1. And then 1 is the only y value that we have right here. So it can be anything less than or equal to 0, or it could be equal to 1. And those are the only options in terms of y values. Just negative values or exactly 1. Okay, other questions on this one? Okay, please flip to the back of number 21. Okay, these ones are inequalities. So that means there's going to be some sort of shading. So the whole back page, there should have been some shading going on. Anytime you have less than, greater than, less than or equal to, greater than or equal to, you will absolutely have some shading. So this one, this bottom one, number 21, it's absolute value. And so the way we were doing it in the notes is you start by plotting your absolute value points. And this is just like 18. It starts off by recognizing that it's absolute value. The parent function would have these 3 points, and then you can figure out how they would transform. So this actually, if we look at this part of the equation, there are 2 transformations, and they're both on the outside, which means they both actually affect the y. So the first thing that we should see is that negative on the outside of the absolute value. So what that does is it multiplies all the y values by a negative. And the next transformation is a -3, also on the outside, so we're going to subtract 3 from all the y values. Think order of operations, multiplication would come before subtraction. So first we multiply by the -1 and then subtract 3. And this is all affecting the y's. The x's will not change. So here this x does not change. So we start with this y value. First you multiply it by a -1 and then subtract 3. So times -1 and then -3, and that'll leave you with -4. Then next point, again, the 0 stays the same. And then this y value of 0, we first multiply it by a negative and then subtract 3. And that leaves you with -3. And here again, x is still 1. And then we start with this y value of 1, multiply it by a negative, and then subtract 3. That would be -4. Okay, so those new 3 points, those are the ones that you're plotting. So plot those 3 points. Okay, so we have those 3 points right there. Now be super careful when you're doing inequalities. Make sure you look back at the actual symbol to see whether the line itself should be solid or dotted. This one, because it's just a less than, it should be a dotted line. So when this inevitably happens on the test that you accidentally draw a solid line instead of a dotted line, just make me a little note. Just draw an arrow and say like this line should be dotted because it happens all the time. All right, so this dotted line right here. And again, if you make that mistake on the test tomorrow, just make me a note. Or if you have pencil, of course, you could erase it, but I know a lot of you write in pen. Okay, so that's the actual line. It's a dashed line. And then because of the less than, we have to figure out where we're going to be shading. Anytime you have an inequality, part of the region is going to be shaded. So we can do a quick little test value to figure out where exactly we're going to be shading. So I would test the origin because the origin is not on the line. So test 0, 0. Just plug in 0 for x, plug in 0 for y. And we're going to try to figure out if that is true or false. Okay, so this simplifies down. We've got 0 is less than. -0 is just 0. -3 would be -3. So is 0 less than -3? No, this is false. So one thing that freaks people out about this is when they get false, they feel like they did something wrong. Getting a false for this does not mean you did anything wrong. It just means that 0, 0 is not shaded. So getting the false just tells you that 0, 0 should not be part of the shaded region, which means you shade the other region. So 0, 0 is not shaded, so that means you shade the part of the graph that does not contain the origin. So you'd either be shading up here if you got a true, or you'd be shading in here like this since we got a false. Okay, looks like our next biggest request is just on the same page up at the top, number 19. Okay, so this one, 19 and then 20, they're both lines. They're both just linear functions, but they're presented in 2 different forms. So the top one, 19, that's presented to you in slope-intercept form. So it's like that mx plus b. So let me walk you through how you would graph that. So this number right here, b, that's the y-intercept. So you can go up to that point, 1, and just start with a single point there. So that's the y-intercept. You know there's going to be a point right on the y-axis. And then the next thing you'd look at is m, which is the slope, and that's 3. So the rise over run is like 3 over 1. So you go up 3 and then over to the right 1 to plot another point. So go up 3, over to the right 1, and then you'd plot another point right there. Okay, so with lines, you just need 2 just to get the general shape and see what the slope would be. Again, be careful here. This is just a less than, so it should be a dotted line. If and when that happens on the test tomorrow, just make me a note. Okay, so dotted line, that just tells us that the boundary itself is not part of the solution set. The solution set is whatever is shaded and then maybe including the line, but this one does not include the line. So 0, 0 is just barely not on our line, so we can still use it for a test. So 0 is less than 3 times 0 plus 1. So 0 is still on the left. The right-hand side just simplifies to 1. So since 0 is in fact less than 1, that's true. And what that means for our shading is that the 0, 0 is going to be included in the shaded region. So the 0, 0 is on this half of the line, so that means we shade this side. Okay, questions on this one? Okay, flip to the front. Number 5 is our next request. Okay, so these ones, stating whether a function is linear or not. Linear means this form that you guys know well, the mx plus b form. So basically, it doesn't have to be given to you in this line, but you should be able to get it into that form if you needed to. So if we look at part A, if you look at this, if you try to rearrange it in any way, there is nothing that you can do to rearrange this equation into this form. Like let's say, for instance, you tried to multiply both sides by x. If you tried to do that, then you would have x times y is equal to 5, and there's no way to separate the x from the y. So here, if it's in this form, your problem is that you can't divide by a variable. If you're in this form, the problem is you can't multiply two variables together. Either way, this one's not linear. Going back to the original, the problem is that you can't divide by a variable. So that's the explanation, and you do have to explain. If it's not linear, it says right here, if no, explain why. So here are some common explanations. Both of these are explanations why it wouldn't be linear. This one, you can't divide by a variable. This one, you can't multiply two variables together. Two other things that could pop up are exponents. If you have an exponent other than 1, it's not linear, like if something is squared or if something is cubed. And then the last one is anything involving square roots. If there are any square roots in your function anywhere, it's not linear. This one, not in y equals mx plus b right now, but you could very easily get it into that form by just rearranging a little bit. So this one is linear. So let me recap with you guys some things that are okay versus not okay. These things are okay. Adding or subtracting. Any type of adding or subtracting at all is totally fine in a linear function. You can multiply by a constant. You can divide by a constant. So like this one, y is being multiplied by a constant, which is fine. In this one, x is being divided by a constant, which is fine. What's not okay would be multiplying or dividing by a variable. Okay, so other questions on number 5? Okay, next biggest would be 20. Okay, so right back to the back. We'll do this next one. So this is nice, like going off the tails of number 19. 19 was in slope-intercept form, so we plotted it this way by going to the y-intercept and then moving up using the slope. This one's in standard form. When you're in standard form, my recommendation would be to use your x-intercept and your y-intercept to plot. If you'd prefer, you can get into slope-intercept form and plot it that way, but I would do x and y-intercepts. So here, x-intercepts, you plug in 0 for y. So if you plug in 0 for y, this term is just gone, and you just have x on the left, and you have 6 on the right. So that's your x-intercepts. For your y-intercepts, you do the opposite. You plug in 0 for x. So if you plug in 0 for x, this term would be gone, and then you'd have negative 3y equals 6. For the line itself, we turn it back into an equation. The inequality symbol just tells us where to shade. So when we're actually trying to come up with the equation, we just turn it back into a line like that. And then divide both sides by negative 3, so we end up with y equals negative 2. So 2 different ordered pairs, one on the x-axis, one on the y-axis, and we can just connect the dots. So this x equals 6, that's our x-intercept right there. And then y equals negative 2 is our y-intercept right here. Before you connect the dots, look back at the actual symbol. Symbol says less than or equal to. So because it does have the or equal to, that means it's a solid line. Okay, and then 0, 0 would be our test point, because again, anytime it's an inequality, that means there's going to be some shading involved. So this, we start with 0 minus 3 times 0 is less than or equal to 6. And we want to know if that's true or false. So the whole left-hand side comes out to be 0, and 0 is in fact less than 6. So that comes out to be true. And if it's true, that means 0, 0 should be in the shaded region. So since 0, 0 is up here, we shade this region. Okay, looks like next is 14, number 14. Okay, this one is tricky to go over because I'm sure many of you guys chose different ordered pairs, which leads to different equations. Let me just show you really quickly. The scatter plot, everyone's part A should look the same as what I'm about to write, and then B and C will be different. So 1.3 and then 29. Right there. 1.4 and 24. Okay, so that is roughly what your scatter plot should look like. Okay, so you guys will have that. You make a scatter plot, you've got all these different points that you plug in, and then you should also have a line of fit. So line of fit is just kind of your best approximation of what a line should look like, and you want it to go basically right through the center of the points, kind of like that. So just right through the middle of the data. If it's not all on the line, which it won't be, like what you guys have is not perfectly linear, try to make it so that about half the points are above and half the points are below. Kind of split the difference between those points. All right, and then what you want to do is figure out which points are closest to the line. So like I wouldn't use this one because this one's pretty far off the line. Anything else is relatively fair game. I would use, let's say this one and this one. So second from the front and second from the back. So that would be this point and this point. Okay, anything too far off the line could end up throwing off your answer for part C. All right, so no matter what points you chose, you're going to set up your slope. So slope would be the first thing that you'd find in part B. And slope is always change in y over change in x. So change in y, we'd have 17 minus 24 in the numerator, and then 2.1 minus 1.4 in the denominator. Or again, whatever points that you had, because I'm sure many of you guys chose a different combination of ordered pairs. So in the numerator, 17 minus 24 is negative 7. In the denominator, 2.1 minus 1.4 is 0.7. For this problem tomorrow, get a decimal. It's going to be way easier for you to deal with it if you put it in decimal form rather than in fraction form. Okay, so this, when you divide this out, you end up with just a nice, neat negative 10. Some of them, I think I saw like a negative 12.7. There's a negative 6 point something. It all depends on which ordered pairs you chose. But the ones I chose actually came out nice and neat. And then you guys will be using this form. This form will get used a lot, so make sure you know that equation because you should have used it several times throughout the practice test. You'll be using it several times tomorrow as well. So the slope that we just calculated goes right here, and then pick one of the ordered pairs. Either one, doesn't matter. Just plug it in for x1 and y1. So we will have y minus, and then the first y value here was 24, so I'll use that one. Slope is negative 10, and then you've got x minus this first x value, which is 1.4. So plug it in, and then you have to get yourself down back into slope-intercept form. So distribute, add, do whatever you need to do to get it back into y equals mx plus b. So over on the right, I'm going to distribute this negative 10. So negative 10 times x, and then negative 10 times negative 1.4. So that's plus 14. And then to get y by itself, I will add this 24. So here y is by itself, and I've got negative 10x plus 38. So for part B, that's the actual equation. And a lot of the ones that you guys have might be similar to this. Two things that you definitely need. This number in front of the x, the slope, it needs to be negative. You may have done something wrong if you didn't come up with a negative number here. And then this should definitely be positive. I think somewhere in the realm of like 30 to 50, like somewhere in there. Oh, I'm just noticing now I missed something here. Describe the correlation. It's basically just one word. It's going to be positive, negative, or no correlation. This one was negative because there's a decrease as you move through those points. So anytime that your correlation here is negative, the slope here should also be negative. Same thing with positive. All right, part C, use the prediction equations, that's this right here, to predict the missing value. If you look back up at the table, there is a missing value right here when x is equal to 2. So you're going to plug in x equals 2 and then simplify it down. Okay, so plug in y equals, we'll have negative 10 replace the x with a 2, and then plus 38. So just simplify that up as much as you possibly can. So we've got negative 10 times 2, that's negative 20, plus 38 is 18. Okay, the 18 fits perfectly well in with this data. We've got 21 and then 17, so 18 fits in perfectly. I don't know if any of you guys did this. Some people came up with like a really low number, like 6 or 8 or something like that. If you came up with 8, it's probably because you used the first 2 points. Let me show you what those first 2 points do. So I don't know how many of you guys did this, but if you chose point number 1 and point number 2, if I connect the dots, look how different this line is from the line of best fit. So if I connect these first 2 points, my graph looks like this, which is very, very different than what the line of fit should actually look like. So that's why I would highly recommend when you sketch in your line of best fit, try to pick the 2 points that are closest to it. If you pick the points that are closest to it, that'll make your answer for C much more accurate. You technically, like if you came up with 8 and you use these first 2 points, you didn't do anything wrong. You're not gonna lose any points, but it will probably freak you out if you're looking at this number and saying like 8, that doesn't fit with the pattern at all. So pick points that are closest to your line that kind of carry on the right slope, and then you won't be freaked out by your answer for part C. All right, any other questions on this one? Okay, next we've got number 1. Back to number 1. Okay, so 1 and 2 both have a lot of instructions, lots of different pieces that you're supposed to be doing. So number 1, first thing says state the domain and range. Okay, so domain is always all the possible x values, range is all the possible y values. These are different than something like a graph that you're making, because there's literally just a finite number of x values and a finite number of y values, and that's it. So you literally just list them out. So for the first one, domain, here are x values. First x value is 0.5. Next x value is 0.4. The next one is 3.1. And the next one is 0.4, but we already wrote 0.4, so you don't write it again. If you have repeats in your domain, you do not write them twice. And then range is all the list of y values. Again, there's a finite number of y values, so you literally just go through and list them. So first y value is 3, and then 2, 1, and 0. Okay, so that was the first part. State the domain and range. Here they are. Domain's all the x's, range is all the y's. Then determine whether each relation is a function. Okay, so this is something that people have a hard time with. A function means that each x value goes to one and only one y value. If ever you have a case where you've got an x value going to multiple y values, it's not a function, and then you don't have to go any further. So this x value right here, 0.4, it maps to 2 and it maps to 0. That makes it not a function. Okay, so when you see that, it's automatically not a function. You don't even have to answer the rest of those questions. Okay, so this is not a function. Because I notice here the last sentence says, if it is a function, then you answer all those questions. So since it's not a function, you can just stop there. You do still have to state the domain and range though, because that was listed first. Writing the domain and range is still part of the problem. And then saying that it's not a function, we've got one x value going to 2 different y values. If you guys remember from that height example, that would be like one person having 2 different heights. Not a thing. For something like number 2, you ended up having multiple x values going to the same y value. That's fine. That'd be like 2 people having the same height. Very possible, very probable actually. Okay, so that's number 1. Next we're gonna sneak in 6 and then 8, and then I think that'll probably be it. So flip the page, do 6 and then 8s. Okay, so number 6 is our standard form. A lot of you guys got it in the right order. So like here's the order, ax plus by equals c. So let's start with that. Start by actually getting it into the order that it's supposed to be in. So what you would do, the y is already on the left-hand side, and the constant is already on the right-hand side, but this x term needs to move over. So if you subtract the 3/8 x over to the left-hand side, it'll look like this. We'll have negative 3/8 x plus the y that was already here equals 5. So this is all in the right order. The x is first, then the y, then the constant's on the other side. But if you guys were going through the notes carefully, there were a handful of rules that A, B, and C had. So first rule is that A, B, and C all have to be integers. Okay, so A, B, and C all have to be integers, meaning no decimals, no fractions. So here, A is a fraction. We can't leave it in the form of a fraction. It needs to be turned into an integer. So what we do, see this denominator of 8s? We go through, we're gonna multiply everything by 8, and that's gonna clear out the fraction. Some people had kind of a good idea with wanting to multiply it by 8/3, and if you multiply this by 8/3 and these, then these would turn into fractions, and then you would just make a mess again. So make sure you're multiplying just by a whole number that will clear out the fractions. So multiply absolutely everything on both sides by 8 and get those integers to clear out. So 8 over 8, this will cancel, and you'll just have a negative 3x left. And then 8 times y, and on the right-hand side, you have 8 times 5. Bless you. So now we fix this. So all integers. That's the first rule. Second rule is that you have to have a GCF of 1, meaning that a, b, and c can't have a common factor that you can divide out. So if we look at 3 and 8 and 40, if they had any common terms, like if they were all divisible by 2 or 3 or 4, if they were all divisible by the same thing, you would have to divide it by that value. But here they're not, so we're actually good on that rule too. And then our last restriction is that the leading term has to be positive. So here our leading term is negative, so you either have to multiply or divide everything through by a -1. So let's say we divide every term by a -1, and that way the leading term will come back positive. So this is now a positive 3x, but it changes the other two. So this is a negative 8y, and this is a negative 40. Okay, last one I'm going to sneak in is number 8, and this is a quick one. Just finding the rate of change. Rate of change is the same as slope. So whenever I give you a table like this is x, this is y, and you can pick any 2 points you want. So if you do just the first two, change in y is 1220 minus 520 over 8 minus 3, and ends up reducing down to 140. And the numerator would be in meters, and the denominator would be in minutes, so it would be in meters per minute. All right.